Okay, our last little review, what we've done over the first couple of weeks. We've talked about the background knowledge, we've talked about arithmetic and geometric sequences and series. We've had a look at vectors. Radians was the last thing we did. We talked about, and what we were doing with radians, it was arc length, sector area, and just angle measure in general. Let's start by reviewing what we know when we're dealing with nice circles, assuming I can get a pretty circular shape out of that. I did pretty well there, I think. So we have a circle with a radius r, and we usually measure angles in degrees. That's fine. We're all pretty comfortable with that. What do we know about the area of a circle? Well, the area was pi r squared. We're all happy with that. And the circumference equals 2 pi r. We were pretty happy with that. When it came to a sector, remember, is part of a circle, and the part that we're talking about is sort of looks like you've cut a slice of pizza out of it. So we're not talking about a segment, which is where we just make a horizontal cut like that, or a vertical cut like that in that case, but a straight line cut. This is cutting out a wedge shape. We were able to find the arc length in this case, so the arc length I'm going to call L. How do we do that? Well, the arc length was a fraction of the circumference, wasn't it? What fraction was it? Well, I measured that angle in there, theta, and I said it's that fraction out of the whole circle, which is of course 360 degrees, and then I multiplied it by 2 pi r. If I wanted to know the area of that sector, what did I do? The same thing. It's a fraction of the full area, so it's theta divided by 360 multiplied by pi r squared. That was all fine and dandy and very good, except for one problem, wasn't it? We're big kids now. We want to be able to use these radians in more places because degrees hold us back a little bit, don't they? Why do degrees hold us back? Because they are not real numbers. They're not in our base 10 number system. They don't fit on our number line in the same way. They don't represent the same thing. We break them up into 60ths and call those 60ths minutes, and then break those minutes up into 60ths and call them seconds. Great for telling the time, great for the purpose they were designed for, but not so great when we're trying to model wavelength and all sorts of other things which rely on things repeating a pattern. So periodic functions they're called, and we'll get to those again, even though we talked about them a little bit last year. So we defined a new measure of angles rather than using degrees, and the measure we used was radians. What was the definition of a radian? I'm going to go freehand here. That's pretty bad. I won't go freehand, just for you. I know some of you like nice, neat notes. On the board, I might be able to draw them a bit nicer. That was pretty ugly, though. Try and draw that freehand one. The definition of 1 radian is the angle made at the center of a circle, so subtended is the fancy mathematical word, by an arc that is equal in length to the radius of a circle. So that angle there, theta, in this case it's 1 radian, so let's actually call it 1 radian. That was terrible. I should have just changed the eraser, but I didn't. Too bad. 1 radian, remember C for the circle measurement. Usually if we don't have anything there, we'll assume it's in radians. But 1 radian is the angle subtended at the center of a circle by an arc equal in length to the radius. Okay, well that's not too bad. We're okay with that. The question was, well, we know there are 360 degrees in a circle. That's a definition we've known for a long time. We didn't even realize that was actually a definition. We just thought that's what it was. But someone had to decide upon that one day. Okay, so there are 360 degrees in a revolution in a full circle. How many radians were there in a circle? That was a bit tricky for us to think about. How many radians in a circle are in 360 degrees? And we remembered that there was one relationship we knew. This was the same, this was an equivalent question to saying how many times will a radius go around the circumference of a circle? And again, that didn't make a lot of sense at first, but when we thought about it, we have a rule that tells us that. We talked about it just before. We've got a rule for the circumference of a circle. The circumference of a circle is equal to 2 pi times the radius. That must mean that the radius goes around the circle, the circumference of the circle, exactly 2 pi times. Therefore, there are 2 pi radians. 2 pi radians is equal to 360 degrees. 2 pi radians in a circle. Or we can simplify that down to pi equals 180 degrees. Now, one day I'm going to go on a little rant and talk about tau and how, had we defined pi as being 360 degrees, it would have made our life much easier. We didn't. It's okay. Life will go on. I'm not going to win the battle, but I'm still going to mention it anyway because it's really good to think about and it's great for your talk. So we will go into that at some stage. But for now, we've got to remember a full revolution, that's 2 pi radians, or halfway round must be pi radians. That was very useful. What were the implications when we got to our area and arc length for sectors? Let's have a look. Here's a sector again. It's that fraction of a full circle, assuming I've drawn that beautifully into the center there. Let's assume I have. Again, when I want to find the arc length, it's a fraction of the full circle, but instead of the circle being 360 degrees, we're measuring in radians now. We're measuring in real numbers. So it's just theta over 2 pi. And then what is my equation for the circumference? It's 2 pi r. And something beautiful happens there, doesn't it? 2 pi in the denominator, 2 pi as a factor in the numerator. Those two things can cancel. So the arc length, when measuring in radians, is simply the number of radians multiplied by the radius. It's that easy. And we didn't quite get to the area one, but I'm going to include it now anyway, because I'm sure you'll have figured it out. The area, it's still a fraction of 2 pi instead of a fraction of 360 degrees. What's my area formula? Pi r squared. So then the area, if I'm measuring the angle in radians, the area of a sector, what's going to cancel this time? Just the pi's. And I'm going to have theta r squared divided by 2. Okay, that's a lot to take in, all those review lessons. Hopefully, hearing it again the second time, having done some problems in between, it's going to start making sense. It will have raised some questions. What are you going to do? I'm going to keep saying it. Put them in the collaboration space. Let me help you out. Come and see me at lunchtime. Let's stay on top of our maths. It's going to make your life easy. All right. Keep up the great work, guys. Cheers.